This lesson, we discuss about the derivation of the Cauchy Riemann equations, the cell called the CREs. So this is how we derive the CREs. Let W equals to f of z equals to u of x y plus iv of x y be an analytic function in a region R. And then when we say that this is just not a function f of z is said to be analytic at a point z equals to z naught if it is differentiable at that point and in the neighborhood of this point. So f of z is analytic in a region R means that f of z is differentiable in R, this region R. So this is what we have. And then other words for the same. The terms regular and holomorphic are also used to mean analytic functions. So we are saying that analytic is the same as regular, is the same as holomorphic. So simply meaning differentiable. So that was just a by the way. So we have W is given by U plus IV. So next point or the next step, the derivation, let delta U and delta V be the increments of u and v respectively, corresponding to increments delta x and delta y of x and y. So delta u, delta v are small positive in increase in u and v respectively, while delta x and delta y small changes in x and y. So then now, f of z plus delta z will be given by u plus delta u, and then plus I into v plus delta v. Since we said f of z is u plus iv. So when you say f of z plus delta z, it should come out clearly that it will be u plus delta u plus I v plus delta v. Now, f of z plus delta z minus f of z divided by delta z will be given by u plus delta u plus I v plus delta v minus u plus iv divided by delta z. Now you see this will be given by u plus delta u plus iv plus I delta v minus u minus iv divided by delta z. I've just opened the brackets. This and this cancels out. This cancels out. So which means that f of z plus delta z minus f of z divided by delta z is nothing but delta u plus I delta v divided by delta z, which now can be written as delta u over delta z plus I delta v over delta z. Now we say that f of z is analytic. So when you say f of z is analytic, you mean that f of z is differentiable. So therefore, limit as delta z approaches 0 of f of z plus delta z minus f of z divided by delta z will be limit as delta z approaches 0. Now we have already found out this quantity to be delta u over delta z plus I delta v over delta z. Or we can write this as f prime of z, because that's what defines this limit, is given by limit as delta z approaches 0 of delta u over delta z plus I delta v over delta z. Let's call this one question 1. Now, delta z can approach 0 along any path. That should be clear. Since delta z can approach 0, along any path, then we have two main cases. So let's say along real axis. So this is the x-axis. It's like we have this case. So this is a point. We have 2 points here, Q and P. So delta Z the same as change in X. So Z equals to X now in this case. So along the X-axis or along the real axis, the imaginary part is 0. So by definition, Z is X plus IY. But on X-axis, remember this is Y, this is X, Y is 0. So this means that Z will be X and delta Z will be the same as delta X, and change in Y is 0. So putting this values in equation 1, we have f prime of Z is the same as limit as delta Z now is delta X approaches 0. So where there's delta Z, you put delta X in this case, approaches 0 of delta U over delta X plus I delta V over delta X, because delta Z is the same as the delta X. And this is actually the definition of partial derivative of U with respect to X plus I partial V partial X. And then along the y-axis, the concept of partial derivative comes in because Z is having two values, variables, X and Y. And then in this case, we use a function of X and Y, but what is only changing X. B is also a function of X and Y, but what's only changing is X. So that's why we have this kind of derivatives. All this one too. Along the imaginary axis, this B, the y-axis, so I have this x-axis, y-axis. So this is the origin. So I have, say, point Q, point P. So here, delta z is same as delta I delta y, because only y is changing. So z is I y. So we know that z is given by x plus iy, but on y-axis, x is 0. So which means z will be x is 0, so just have iy. So which means delta x is 0 because there's no change in x, and delta z is the same as I delta y. Now, putting these values in equation 1 again, we get f prime of z is given by limit. Now delta z is the same as delta y approaches 0 of now delta u over I delta y plus I delta v over I delta y. So which will give us limit as delta y approaches 0 of now negative I delta u delta y plus delta v delta y, because now we have cancelled I and I. So remember what you have, this was delta z, so delta z was replacing I delta y. So this is the definition of negative I partial u partial y plus partial v partial y. And I still repeat, the partial derivative is coming in because u and v are depending on both x and y. While in this case, only y is changing, so that's why we have this case. Call this one 3. Now, since f of z is analytic, that simply means differentiable. Then equation 2 equals to equation 3, because all of them are defining the derivative. So that means partial u partial x plus I partial v partial x equals to minus I partial u partial y plus partial v partial y. Now these are just complex numbers. And then for this, actually this equation can be written as partial u I-e partial u partial x plus partial v partial x I equals to partial v partial y minus partial v partial u partial y times I. So equating real and imaginary parts, we get partial u partial x equals to partial v partial y and partial v partial x or partial u partial y equals to negative partial v partial x. So remember this and this is the same as this negative. So partial v partial x is the same as negative partial u partial y. So when we make this partial u partial y the subject, then negative will be on vx. So these two equations are what we call the Cauchy Riemann's equations, CREs. So these are the Cauchy Riemann's equations. So if I call this one equation 4, so 4 are called the Cauchy Riemann equations. And actually, they provide a necessary condition for any function f of z given by u plus iv to be analytic. So simply, that's what you mean is that for f of z to be analytic, then the two Cauchy Riemann equations must be satisfied. We'll be proving the analyticity of functions in the next session. But that's how we prove Cauchy Riemann's equations. Thank you.